Hello everyone. Good day. This is Jared De Leon Taay. And at this time po, we're going to talk about probability, factorial rule, permutations and combinations, law of large numbers, Bayes' theorem, probability distributions, and central limit theorem. First, at this time, we're going to talk about what probability is. We will also calculate probability, and then we're going to talk about a little bit about zero probability. Okay, just like a chance of a high schooler like dating Beyonce or something, just like that's like a zero probability. So we're going get into uh to get as well. All right. So what is probability? Probability means the favorable outcomes over all the possible outcomes. In other words, it means what is you're looking for the chance of happening over all the other possible options or other options. All right. So here's an example just to show you or to illustrate how that works. First, if I roll a dice, what is the probability that I will roll an even number? So we're going to look at the favorable outcomes, the things that we're looking for over all the other total possibilities. And here are some questions that can guide us. So first of all, first question is how many even numbers are there? So on a dice, you've got a cube here, and there is a six side of it. How many even numbers are there on the dice? Well, there are 2, 4, and 6. Those are even numbers. So there are 3 even numbers on a dice. How many total numbers are there on a six-sided dice? So we have 1, 2, 3, 4, 5, 6. There are 6 total numbers. So the way that we look, what we're looking for is how many, what's the probability that I'm going to roll an even number. So how many even numbers are there? So we have 3 out of 6. So my chances are 3 out of 6. So I can reduce that to being 1/2. In other words, the probability of me rolling an even number is a 1/2. I can either roll 2, 4, or 6. The other things I could roll would be 3, 5, and 1. So um, let's calculate some probability. Okay, the probability is written like this: P with uh, open and close parentheses of event or the probability of that event. So here's an example from the previous questions. I would have the letter P, and then in the parentheses, I would say even. That means the probability of rolling an even number. So whatever inside the probability, inside the parentheses, there's that what you're looking probability of this happening. Okay, so all right. So let's calculate some. Here is a spinning cube. So imagine that green arrow. I can flick it with my finger, and it will spin all around. What I'm going is I'm solving for the probability of a blue. Again, what P with the parentheses, it means the probability of the spinning blue. So if I were to spin the spinner around and all the parts are equal, there is one space that is blue, and there are 4 total spaces. So I would say the probability of rolling a blue is 1 uh, out of 4. And there's one space that's blue and 4 total spaces. That's how we calculate the probability. Next one, Let's take a look at our next slides with the funky colored spinning circle. um, and uh, what does what that means is P. With the red is the probability of spinning the red. Part of the challenge of the learning probability is learning the way that we write the probability questions. P red, what does that mean? The probability of spinning red. So you think about the spinning that comes now. A yellow spinner, around how many red spaces are there? And how many total spacers are there? The probability is there are 3 red spaces out of a total 8. So the probability of roll of spinning red is 3 out of 8. There's 3 that are red and there's a total. Again, what you're looking for goes into the numerator and the total possible outcomes are in the denominator. First, let's calculate one using a dice or a six-sided number cube, whatever you like it to call. So the next is, I just want to emphasize the notation of the P2, which means the probability of rolling a 2. What is the probability of rolling a 2? Well, there is one, number 2 on the six-sided dice. There are 6 total sides, so my probability is 1 out of a 6. Okay, so there's one, number 2, and there are 6 total sided. Okay, so my probability of rolling a 2 is 1 out of a 6. That would be actually be the probability of rolling any of the numbers. The probability of rolling a 1 is, there's 1 out of 6 as well. Okay, so that's how we calculate probability. Okay, so the final things we're going to talk about is the zero probability. Again, the chances of a of of dating a rock style while you are in high school probably not gonna happen. Alright, so here's what the zero probability. Here's an examples. I want to solve you for the probability of the spinning yellow. Well, well, that's easy. As you can see, there's no yellow spaces out of a total 8. So our probability is 0 out of 8. You can write it as 0 out of 8, or you could just say the probability of the spinning yellow is 0, because 0 divided by 8 will give you 0. This 0 probability is like flipping coins and trying to get a green. You know, likes heads or tails, it's not green. So that's the same thing with this. If there is no chances, like there's no options that are favorable, what you're looking for, then you have the zero probability, and this happens from time to time. Just to keep and be aware of that, and that is possible to get a zero probability. It means that there are no favorable outcomes. There's no way that you can get yellow when you're spinning around on this. With green, red, and blue. Alright. We'll talk about what probability is our favorable outcomes over total possible outcomes. Okay po. The next one is we're going to talk about the another example of a probability using a word problems. Okay. Show you how to calculate the probability and then switch into word problems. Word problems are gonna make up the majority of the problems that we look over today. Now, when we're talking about the word problems with probability, you're doing the same thing. Only you're talking all your information from the word problems. So first, let's take a look. If there are 3 marbles, 3 red marbles, 2 blue marbles, and 1 yellow. Okay, yellow in a bag. And we're going to solve for the following probabilities. Okay, so this one here is the probability of drawing a red. So the probability of drawing a red, and there are three red marbles and 6 total marbles, as you can see. So my probability of drawing a red is 3 marble out of 6 when I reach my hands in there to draw out a marble. There are 3 red marbles out of 6 total marbles. Now we can leave the questions like this. We have to reduce it down to the lowest terms. So I'm going to divide it both of them by our greatest common factor. Okay, leaving us with 1/2. Half of the marbles are red. Okay, as you can see naman po. And that is how we would solve these probability questions with the marbles. Okay, so our next probability or problem is the same situations, but now we're solving for the probability of the blue marble, which is we have the same bag. Okay, solving for the probability of blue, there are 2 blue marbles out of our totals of 6 marbles. So the probability of drawing the blue is 2 out of 6. Now we're going to reduce that down to the lowest terms by dividing by our common factor of 2. Common factor of 2. You have to remember to reduce these fractions down to the lowest terms. And also, it helps us to keep things simple. So that is the probability of drawing of blue marbles, and those are the 2 questions we're going to do with this bag of marble. Okay po. So the next type of question is based on an amazing book. If you took the book title, which is the Kingdom of Denal, and each letter has made into a card and put into a basket. Next is, what is the probability that you'll reach in and draw out the letter N? It is a little bit complicated, but we just write it as this. Solve for the probability of drawing an N to help illustrate what the way that I would do it. Okay, so I'll go ahead and write the title of the book, The Kingdom of Tenal. And now, what I'm going to do is to illustrate the times that the letter N appears. So it appears 2 times, as you can see. The letter N appears 2 times. And there are total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 letters. So that's the probability. Then the probability of drawing out the letter N, if each letter has drawn out at the random, is 2 out of 15. And then that's how we would solve this with the book uh, um, uh, the title, the book title, Kingdom of Dinan, 2 out of 15. Next naman po is, let's try another type of word problems. Okay, so a month problem. Month. What is the probability that you are born in a month that ends in ER? Now, that's kind of a funny question because obviously you know what month you're born in. But if I didn't know you and I will try and to make a guess, what's the probability that you were born in a month that ends in ER? Okay, so I'm solving for the probability of the month ending in ER, and the way that I would do this is probably list all the months and see how many of them end in ER. Well, I've got September, October, November, and December. Okay, that's all end in ER. So there are 4 months that ends in ER, and there are total of 12 months in a year. The point is that the number of the months and ends in ER are 4, and the total number of months are 12. So the probability that if I choose a month at random that you were born in, and the chances are 4 out of 12. That you were born in a month that ends in. So I would reduce that down to the lowest terms and find that 1/3 of the month in a year and the year that ends in ER. So next one, our final questions is a little bit a trick questions. So try and see the trick in this. Okay. In a pet shop, In a pet shop that sells only dogs and cats, there are 24 animals for sale and and 10 are cats. If I choose an animals at a random, I want to solve for the probability that the animals will be a dog. Okay, the challenge and trick with this is right here. Okay, I never give you the number of dogs. I never told you how many dogs um, are there in the pet shops. But the informations in the word problems gives you enough information so that you can solve it. So the trick with this really is that is to get people out of the habit of just writing down the two numbers that you see. If you wrote 10 and 24, no matter what order you wrote them, you would get this question wrong. So you have to carefully read and figure out that there are 14 dogs 14 dogs, the total number of animal is 24 rather, and 10 are cats. If we subtract, we'll get that 14 of these are dogs, and there's 14 dogs and 10, so the probability of selecting a dog when we pick an animal at random would be 14 over 24. And if we reduce that down to the lowest terms by dividing both the top and the bottom by 2, and our probability is 7 out of 12. So again, look for those three questions. Okay? Look for those things and be expecting to see some questions that might be a little bit more tricky. Okay? Okay po. So let's proceed to the third part, which is the permutations, combinations, factorial, and the probability. First, let's define what is a permutations. Well, a permutation is essentially an ordering of objects or items or letters. It is an ordering. So when we talk about permutations, let's take an example. Say, for example, we take the word cat. Okay. We take we take the word cat and we want to see how many different ways could we arrange these three letters to make essentially a new word using all these three letters. Okay, so let's take a look at that. Okay, you can see that you could write this as, of course, cat would also say um, C T A. We would A T C A C T T A C and T C A. Okay, so you can see there's an equals 1, 2, 3, 4, 5, 6. actual 6 different ways of writing this. Word using all 3 letters in the word cuts. So there are 6 permutations or orderings. Now there's another way to do this when you're talking 3 items. Okay. So and when you're wanting to see how many different ways you can order them, or you can use this formula which is the factorial. Okay. Factorial. Now, the way the factorial works is you start at this number here. In case where 3 letters, that's gonna be okay, so let's write first 3 factorial, and you take that number 3 and you multiply down to a 1. Okay, 3 to 1, which is equals to 6. Now, the another way to look at this is oftentimes is this which is referred to as the fundamental counting principle or the multiplication counting principle. And basically what you're doing is you're saying for each category here, okay, for each letters, okay, okay. So well, there's are 3 choices for the first letters, okay, in your word, but once you use the letters, now there's only gonna be 2 choices for the second letter. And then once you use up those 2, there's gonna be 1 left for the third. Okay, so it's 3 times 2 times 1. 3 times 2 times is equals to 6. Okay, so we'll do to illustrate. Right, so let's draw here. Is to have you to draw a tree diagram. Okay, so and I'll just show you that in real quick. So for the first letter, you could choose a C, A, and the last is T. Once you choose C, you have 2 choices. You could choose um, A or T. And if we choose A, so you have 2 choices. It's gonna be or C, T. Okay, and if you choose a T, we have choices, and there's gonna be okay po. If you choose a T, you have 2 choices, and there's gonna be a C or A. So if you're going to uh so if you're going down this branch, you can see if you've chosen C, you've chosen the A. The only letter left would be T. Okay, so here you have a okay, so that's the idea. Now what happens if you wanna take the permutations of the n and objects are at the same time. Say for example, if you wanted to make like a 2-letter word using these 3 letters, well, walks in the NPR. Okay, so what is NPR? So NPR means out of n objects, how many ways are there to pick R of them? Okay, Okay, so where the order's importance. Okay, and there's a formula that you're gonna memorize, and we'll talk about this in a minute. It's a okay, wait a second. So I'm going to erase muna the the diagram. Okay. So these are the formula: n factorial over open and close parentheses n minus r close parentheses factorial. Okay, so let's do an example. Okay, so say we want to make a 2-letter out of a 3 letters in the word cut. So let's just write for a minute. So um we would have the CA, we would have the CT, CA, the CT, we would have else we have the uh okay, CA, CT, we will have the AC, we will have uh the AT, and we have the TA. Okay, so as you can see, there's a 1, 2, 3, 4, 5 TA, and the last is the TC. Okay, so you can see there's 6 possible ways of making a 2-letter word where the order's important. Okay, so CA is different from the AC. Now we're going to talk about in just a minute combinations where the order is not important, and we'll talk about that in just a second. But notice here, there's another way to calculate this instead of writing all this out. We can use the forms that we can say out a 3 letters, CA and T. We pick the two. Okay, now I'm just using the word pick just as a way of thinking about this. Out of the three items you wanna say, um, how many ways are there to pick the two where the orders are important? Okay, so let's wait a second. Wait lang, wait lang. Okay, okay. So I want to say how many ways are there to pick up the two is important. So for example, so we have here the uh 3 P2 is equals to 3 factorial. Okay, you can see the AC and the CA, and there's actually the same 2 letters. So we have 3 minus 2, when it plus parenthesis factorial, is equals to 3.0 times 1 over 1 is equals to 6 over 1, or just simply the 6. Okay, just simply 6. Okay, so you will get the 3 times 2 times 1, which is 6 over 1, which equals to 6. Okay, different ways of picking 2 letters. Okay, out of the three letters that we started with to make a words where the order's important. Now, say for example, the orders are not important, so this is when we're gonna be talking about the combinations and the combinations. Okay, you can see that the AC and the CA, these are actually the same two letters. For example, if you're gonna pick up, the two items out of the bag of three items, it doesn't matter. Okay, if you pick C first and then A, or first and then C, because you're gonna end up with those two items anyways, with this the T or the AT. Okay, so we would only count this as one results. Okay, or one combinations. Same thing here. We got a T. We have the TA or the AT. Okay, the AT, and then we have the CT and the TC. So you can see we've grouped those together. So there's really only three unique outcomes, as you can see, the three distinct outcomes, and the way we would this is we have used our combinations formula, which is the let me erase first, which is the um n factorial CR. Okay, n factorial over n minus or factorial. Okay, so now notice how this formula and this formula, they're almost exactly the same. Okay, kita naman po natin. The only difference is that we're dividing by this r factorial. And what does this mean? And is that we're dividing out the duplicates. We don't want to count A, C, and the CA as the same. Okay, so we're doing is where it's different. I would, or I should say, they're the same. So we want double count those. And also we want to divide out those multiples is this. So in this particular example, we have the three letters. The three letters, for example, 3C2. 3C2 is equals to 3 factorial over 1 factorial multiplied by 2 factorial. Okay? C, C80 we're choosing 2. Okay, so that's just one way of thinking about it. Out of 3, we're choosing to the orders not important. We just wanna find out how many different outcomes there are. So that's gonna be the 3 factorial over 3 minus 2. Okay, which is 1 factorial times 2 factorial. If we expand this out, we get the 3 times 2 times 1 over 1 factorial. Okay, 1 factorial, which is 1, 2. Okay, factorial is 2 times 1. Notice the 2 and the 1, they cancel. 3 divided by 1 is equals to 3. And that's what we found out there. That's there be actually 3, the groups of those two letters. Alright? So that's the idea between the permutations, combinations. But quickly, I just wanted to go back here for a moment. We're talking about this formula n factorial. Um, n factorial. So the n factorial represents, how many ways are. Okay. Okay. N factorial. Okay. To arrange all n items, so for example, if we have like a word, say for example, the math, okay, math word, math, math, and we say, well, how many ways could we arrange all of these letters? Okay, you can see, as you can see, there's a four letters, so we would say that this is the 4 factorial. 4 factorials, that's gonna be 4 times 3, 4 times 3 times 2 times 1 is equals to 24. Okay, okay, so we have 24 different ways to use all four letters and rearrange those letters. Okay, a different so-called words, it might not actually be a words, but it look like, like a four letters, okay, in a different order. Now, another way to do this problem is to use the permutation formula, the NPR formula, and NPR. The only difference is we would be saying 4 4 4 P 4. So we'd say out of four letters, we're gonna pick 4. Okay. So basically all of them, and if we use our formula, you can see this is gonna be the 4 factorial over 4 minus 4, 0 factorial. 4 factorial over 0 factorial. I'm just doing the n minus r but 0 factorial. This is gonna be this one that you're gonna want to memorize. Okay, 0 factorial is equal to 1 4 1 factorials. Okay, so you aren't gonna memorize that. So you can see the 0 factorial is 1. So we end up just 4 factorial like we have up here, which is the 24. So the two different ways to do it, you can either use a formula n factorial, or you could use the NPR. Okay, the NPR formula. Now, if you took a words like the algebra, algebra, and you want to find out the number of permutations of all the letters in the word algebra, you can see that there's a 1, 2, 3, 4, 5, 6, 7 letters. So there's gonna be a 7 factorial ways. Okay. Yes. Rearranging all 7 of those letters, but notice how that there's a 2 A's. Okay. Okay, first and the last. So when there's a multiple letters, there's repetitions. What you want to do is you want to divide out those multiplicities. So in this case, because there was a 2 A's, okay, 2 A's, okay, so we're dividing by the 2 factorials. 2 factorial just 2 times 1, which is 2, 7 factorial over 2 factorials. And you can see that if I was to, put this A here, okay, here, and here, it would be still look like a word algebra. So we don't want to double count that. Okay, this thing as a, the same when we wanna count it as separate permutations, right? We don't want to basically treat that as a different words. Okay, it's gonna look like the same words. We want to divide out those multiplicities. All right. Okay, next one. Okay po. I'm going to erase all muna. Erase those. Okay, written. Okay, next one is let's take another examples like a uh Mississippi. Mississippi, Mississippi. Okay. Mississippi. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so this one has 11 letters, so there's gonna be 11 factorial for ways of arranging those 11 letters. But notice we've got 4s, as you can see. 1, 2, 3, 4. Okay, this one and this one. So we're gonna divide by 4 factorials. Okay, 11 over 4 factorials. Okay, and also we got a 4 eyes. Okay, so we have 1, 2, 3, and 4. 4 eyes. Okay, we got 4 eyes. We divided by the 4 factorials, and we got 2 piece. So you can see 2 piece. 2 piece. And we're going to divide by the 2 factorials. And again, all this is it is a dividing out those multiplicities. Okay, 4 and 2. So 4 factorial, expand this out 4 times. 4 times 3 times 2 times. Okay, and 1 again, another 4 times 3 times 3 times. Okay, 1 times 2 times 1. Just simply um, and also you don't want to make a mistake of saying the 4 times 4 and this is 16 factorial. That's not correct. You have to do this individually. 4 factorial, expand this out 4 times 3 times 2 times 1. Again, another 4 times 3 times 1 times 2 times 1. And just simply and then you can divide, and that's gonna be the number of the distinct of the different or the unique, however you wanna permutations of all the letters in the words Mississippi. Okay, so next one, so let's go to into the sum word problems. If you can see, okay, so you may do this along with me here. Okay, it says if there are 10 people in the committee, how many ways are there of choosing a president, vice president, and secretary? Now at this point, we're just talking about the number of outcomes. We're gonna get into the probability in just a little bit here. But first, we wanna find out how many different ways there are of choosing the president, vice president, and secretary out of the 10 people in the committee. Now, uh, now the questions that you wanna really focus on is the order important or is the order not important? Well, if you were to take 10 peoples and you're gonna basically pick 3 of them, 10, okay, 10 people and the 3, if we're going to pick 3, well, if you were take 10 peoples and you're gonna basically pick 3 of them, okay. If you change the order of those people, they're gonna have a different job or the different positions. So the order is important. This is gonna be the 10 permutations, 10 is equals 10 over 7 permutation and 3, or the 10p3, or sometimes what I say is out of the 10, you're picking the 3 where the orders matters. Now, if we use our formula here for a permutations, you can see this is gonna be 10 factorial over 10 minus 3, which is 7 factorial. Okay, and if we're gonna expand this out, it's gonna be a 10 times 9 times 8 times 7, 6, 5, 4, 3, 2, or just rate that 7 factorial over 7 factorial. As you can see, 7, 7. As you can see, those are canceling. So it's literally just gonna be 720 different ways. Now another to do this is to use the multiplication counting principle or the fundamental counting principles, and you can see that there's gonna be the 10 ways of choosing the president. Okay, but once you choose the president, there's only 9 people left. In this group to choose the vice president, and then once you choose those 2 people, there are only 8 people remaining left to choose the final positions, which is the secretary. Okay, 10, 9, 8. And you can use the multiplication accounting principle or the fundamental accounting principles and multiply those together. You're gonna get the same results. A lot of students prepared this method because it's just a kind of easy way of thinking about it. Okay, you say out of 10, you're picking the 3 where the orders matters. But for others, this is a little bit easier. Okay, so next one, so let's take a look the number 2 example. Now it says that there are 30 people in your tennis team. How many ways you can choose to co-captains? So my question is, do you think that their order is important, or do you think the orders is not important? Well, in this case, the order, it doesn't matter, but if you take her, this person and this person's, and you switch them, they're still gonna be the same co-captains. So it's not like they're gonna have a different positions, like one's are the presidents, one's the vice presidents. No, they're the same positions. It doesn't matter, in what order we choose them. So we're gonna use the combinations. Okay, so 30 combination. So we have the 30. Okay, co-captain. We're going to choose two. Uh, where you could say that out of 30, we're choosing two. Okay, 30 over, open close parenthesis, 30 minus 2 factorial 2. 2 factorial. which is the 3 factorial over 30 minus 2 factorial, 2 factorial. So this is gonna be a 30 factorial over a, okay, 30 factorial over a 28 factorial with 2 factorials. And again, notice this 2 factorial, what this is doing is it's dividing out those multiplicities like the A and B and the B and A. Those are the same two peoples but are the same co-captains. You don't want to double count those, so that's why we're dividing those out. So you can see this is gonna be the 30 times 29. Okay, 30 factorial 28 factorial 2 factorial. You have 30, 29, 28 factorials. Okay, all the way down, down to 1. Okay, over 28 factorial. Okay, so next one is we have here, those are canceling over the 2 times. Okay, over the 2 times factorials. 1, and you can see those 2 goes into 30, 30, 15 times. So we really just have 15 times 29. Within just 29, and it's gonna be the number of ways that you could choose those two co-captains. So let's take a look at the number. Okay, so let's take a look at number 3. It says if a board has a 10 women and 7 men, how many ways can you form a committee that contains 4 members? So this is a very important 4 members such that all 4 are men. Okay, so what do you think on that one? So all 4 are men. Well, you can see there's a 7 men. So out of 7, we're gonna be choosing 4. And I'm using the combination 7, combination 4 because the order doesn't really matter. It's just a committee. It's not like they have the president, vice president, or the vice president, or the first place, second place, third place. The order is not important, and you can simply just using the combinations of the formula here. So this is our formula. NCR is equals to, oh wait lang. Okay. NCR is equals to n factorial over n or factorial or factorial. So simply means 7C4. Okay, the answer. Now, so let's take a look at number or letter B. Okay, it says 2 men and 2 are women. Well, again, what do you think or what do you do is to take how many there are in a group. There are 7 men. There are 7 men, but we're choosing 2. Okay, but we're choosing 2, and there's 2 that are women. Okay, so that so of the 10 women, we're choosing 2 and we're gonna multiply those 2 together. So we're using the fundamental accounting principles. Okay, so we're basically saying, how many outcomes there are in this group, times how many outcomes there in our times are in this group, and we're multiplying them together. Okay, so the last one, The last one, this one is a little bit more challenging because it says at least one is a woman. So at least one, um, it means one could be a woman, two could be, woman, or three or four, all four. Now, we could do it, by individually add them. But another way to do this, when you see this phrase, at least one, you might wanna take notes on this one. But at least one, what do you do is you take the total minus none. Okay, total minus none. Okay, so what does it mean? It sounds a little cryptic. Okay, the next one is how many ways can you find, how many ways can you find a committee of 4 people out of 17 people? Okay, that's gonna be 17. Choose 4 minus the committee that have no women on them. Well, the committees have no women on them would be a 17 choose 4. Okay, 17C. 4, that would be out of the 7 men. Okay, so you're choosing 4. Okay. Now, another way that the students like to do this too is you could say, well, out of the 7 men, we're choosing the 4 times out of 10 women. You're choosing 0, but 10 choose 0, just 1. So 1 times anything is itself, but it's kind of a little quicker way of doing these problems. Okay, do the total minus no women. Okay, 7C4 7C4 multiplied by 10, just choose 0. Okay, it would be all the committed that have at least 1 or 2 or 3 or 4 on them. Okay, so now some example for the cards playing. Um, playing a deck card. If you are not familiar, it is pretty easy to understand. Okay, so for your information, a deck cards have a 52 cards. Half are red and half are black. So 26 red and 26 blacks, and then it could be breaking down into what they call suits for suits. Okay, so it have a 13 diamonds and 13 hearts. These are reds, and also there is a 13 clubs and 13 spades, and those are blacks. Okay, so it have an a king and a queen and a jack. So they call these faces cards because they have no faces on them. Okay, so in each of the different suits, and then there's a numbered cards 2 through 10 in each 4 suits, and then each suit has one faces or the letter A. Okay, so let's go into some example here. It says, how many ways other of being dealt 5 cards hand out of the standard 52 card deck if all cards are 8. So the first one is if all cards are diamond. Okay, so we're trying to figure out how many ways you could be dealt all the diamonds. Well, the key is you say, well, how many diamonds are there? So we have, there are 13, 13 diamonds, and we're choosing 5. or you could say 13 combination 5. Now, it doesn't matter which way you're dealt the cards because you can shuffle them up in your hands once you get them. So that's why we're choosing a common combinations and not a permutations. So this is just a 13 choose 5. Okay. Next one is how many ways are there of getting a 5 cards that contains exactly one face cards. Okay, contains one face cards. Okay, so we look at the face cards. You can see there is a um 3, 6, 9, and 12 face cards. That's gonna be a 12. Okay, choose one. We have 12. Choose one. See exactly one face cards, but then remaining cards there are 40 cards and are not face cards cause a 52 minus 12 which is 40 40 and we're choosing 4. Okay, so one way to think about this is the first number is how many is in the group. Okay, the next is the second number is how many you're choosing out of a group, and then you can see here the 12 and the 40 that adds up to 52. The number or the 1 and the 4 adds up to our 5 card hand. Okay, next one, the next one, let's say you're gonna find out the number way of not getting a queen. So you get a 5 cards in your hands, none of them are queens. Well, let's see. It looks like there's a queen 1, 2, 3, and 4. So if we take the 52 minus 4, okay, 52 minus 4 is equals to 48. That's 48, and that are not queens, and we're choosing 5. We're choosing 5. Okay, all are hearts or all are spades. Now in math, you can see the word or the means a union. It means both. It means like you're combining all these possibilities with all these possibilities, making sure not to double count any, but in this case, you're not gonna get a heart and spade at the same time. So it was a number of ways of getting all hearts. So all hearts. Well, you can see there's a 13 hearts. 13 hearts. So that's gonna be 13. Choose 5 plus. How many ways if they are getting all spades? Well, there's also 13 spades over here. That's gonna be 13. Choose a 5. Choose 5. Choose 5. Okay, do it separately and then add them together. Okay. So next one is how about this the last one. Okay, one club. So at most means that you could have a 0 clubs or 1 club. So let's figure out how many ways of or to get a 0 club. Okay, so you can see there are 13 clubs. So let's just say out of the 13 clubs, you're going to get a 0, but one of the 39 remaining cards that are not clubs, so you're going to get a 5. Okay, okay, 13 choose 0 multiplied by 39 choose 5. Hmm. A lot of 13 clubs were choosing 1, and then the 39 non-clubs, okay, we're choosing 4. Okay, so it's gonna be 13 plus 6 multiplied by 39 I choose 4. Notice the 1 and the 4 add up to our 5 card hand, and there are 39 and 13 and 39 add up to 52. Okay, so let's transition into probability now. Same standard of dealt cards. What is the probability of being dealt all number cards? Now, a quick review of a probability. Probability, as you know, is defined as what the number of the successful outcomes. I'm just gonna write the number of success probability is equals to success divided by the total possible outcomes. Okay, possible outcomes. Pangit ang sulat. Outcomes. Okay, so another way to think about it very simplistically is you know how many ways can you get what you out of the total things that could occur. So it is the number of the success over the total possible. So what is the probability of being dealt all number cards? Okay, well you can see the number cards are 2 to 10 through to 10, and there are 9 number cards in its suits. 9 times 4 is 36. Okay, so we're gonna choose 5. 36, choose 5. Okay, 5 of those, but in the 52 cards. Okay, how many ways you could deal a 5 card hands? That's gonna be 52. Okay, 52, choose 5. Okay, so out of 52 cards, how many ways of being dealt the 5 cards? The order is not important, so we're gonna use in the combinations against, but our successes are 36 numbered cards. We want to choose 5 out of those, so the number of success divided by the total that's gonna give you the probability. And this one, okay, so this one, what is the probability of getting at least one ace? Okay, so the probability of getting at least one ace means that you could have one ace, two ace, three ace, or four aces, or five aces. Okay, that's a lot of calculation. So let's go about it a slightly different way. So let's figure out all of the 5 cards hands. That's 52 cards. That's a 52 cards. That's a 52 cards. Okay, choose 5. Okay, so let's read. The 2 card, choose 5 minus the ones that have no aces. So we have 48. Okay, 48 are not aces because there's a just 4 aces, so we're going to choose 5. Choose 5. Okay, so this would be all the cards that the 5 cards hands that have at least one or more ace in its host. This is the ones that have none. So the um 52 cards 5 minus 48, choose 5 over, okay, the total minus none divided by how many ways that you can be dealt a 5-card hand. The 52 cards, that's 52 cards. Okay, 52 cards. Choose. Choose 5. If you simplify that, that's gonna give you your probability. Okay, so let's talk about the law of large numbers. This is not too difficult of a concept to understand. Um, it has to do with the probability, and it's definitely important that you learn and understand, but it's not that difficult. Okay, so let's get into the law of the large numbers. So this is actually, it's a pretty, the probability principle that has to do with the probability. Okay, so when you study the subject of probability, for example, what's the probability? Let's say, if I have a coin, for example, this is a coin. Okay, so let's say a coin has a head or a tail. Okay, so tama. If I say what's the probability if you flip the coin, okay, so in the air, it's going to lands on heads. Okay, most of you probably gonna be like, well, there's a there's a 50 chance of the chance of 50 chance. Okay, so say you go only two outcomes here, and when you flip this, you got a 50 chance of getting heads or a tails. So the probability, we're always trying to determine or predict outcomes, but when you study probability, we're basically look at the probability in two different ways. For example, this is a probability two different ways. Okay, let's kind of structures. Well, let's just kind get layout into the different manner. So we have, we call the experimental, and the second one we have the theoretical. Okay, so I'm just kind of abbreviating here, but hopefully get the gist of what I'm saying. So the experimental and theoretical are the different. Okay, so let me kind of use example this, the heads, the heads and tails. So if you wanted to know the theoretical probability of flipping this coin, okay, and it's landing on heads, well, we've already determined if determine it, uh, and we have one, oh, okay, one half, okay, so one half uh, chance, or the 50% probability that's going to occur. So let's suppose we're kind of messing around with these coins. So we are actually starting running an experiment, and you flip the coin and you get tails. You're like, okay, well, it didn't turn out the way. It's, I still have the 50% chance. So on my trial, my experiment, it should be, should hopefully get heads. Way, next one, okay. So the next time you flip the coin, okay, and then you get uh, keeping tails, okay, okay, tails, and you're like, well, what's going on here? That's not quite exactly what you expected. Okay, maybe you're on this bad streak, and you're like, oh man, I can get heads. I should, I have 50% chance of getting this, to become ahead, but I am landing with all these steals. So this kind of unexpected outcome. Okay, so your run experiments on your experiment is not kind of like, matching what your theoretical or mathematical probability is stating. So when you study the probability in pure mathematical manner, we really get into what we call theoretical probability. But experimental probability is important because if we're running those experiments and not matching up what we expect, well, then there's a disconnect. Okay, so this where the law of the large number comes in, and it says outcome, your expected outcome here is not going to necessarily match up perfectly with the theoretical expected outcome. So expected 50% of the time that you're going to get hits. Now I ran 4 trials here, so you would expect the 50% chance. Maybe half of these trials or those trials should have showed up heads, but it didn't. Okay, so you're like, well, what's going on? Well, here's the deal. The law of the largest number basically states that you're not going to your experiment. You're going to experimental outcomes. It's not going to get to be necessarily close to the theoretical outcome unless you run a large numbers of trials. So here I've only run 4 trials, but let's say I conducted experiments out like 1,000 times. Okay, 1,000 times, and when I did this, flip the coins, and now we're measuring, recording heads and tails. Now, when I've done that, when I'm recording this and done the experiments of 1,000 times, it's going to be very close to 50%, close to 50% of the time. It's going to be heads or tails, depending. Okay, and if I run out this even larger, like 100,000 experiment, it's even going to expect it to become even closer to our theoretical outcomes. So we have experimental outcomes, or the expectations. This is like a real worlds of stuffs. Like we're running experiments, we're expecting these experiments to have the results of what kind of we kind of calculated in advance. Well, that's only going to be the case if you run the large number of trials. If you're not only have a few um, trials in your experiments, and it's not coming out to be what you kind of calculated with the probability. Okay, well, that's because of the large numbers. Okay, so all right. So again, take our little coin here, and we expect the 50% of times we're going to get the heads or the tails. Okay, so and if we only run a few trials and we get a bunch of tails, or like what's going on here, we should have we have gotten at least some of heads and some tails. Well, again, the larger the number of trials you conduct, the closer the outcome is going to get become to the theoretical probability. So big concept of probability, and this a large topic and of itself, but it is important that you understand it, and it's not that difficult. So when you look at the general the concept of. Okay, so let's continue. So let's continue. Okay, so another topic to be discussed are the Bayes theorem. Okay, Bayes theorem is not only is one of the most interesting topics in the probability, which uses some of its core concepts. It also becomes an important topic when it becomes to a test, exams, and at times in the interviews. People oftentimes find it tricky and at times confusing. So, but I hope these discussions will help you to find what you can solve very complex problems with easy way. Okay, so let's start it now. This is clearly beyond tossing the coins and rolling a dice. If you study the basic probability, you would know what happens when um, you flip a coin, what happens when you roll a dice. But there's are concepts which could be tricky at times, and that's where your examiners or interviews try to differentiate between the persons or who just has a superficial understanding of the subject versus a person who really understood the core concepts. Now, before we move any further, let's understand so why probability becomes so important and when it comes to data. Probabilities lead us to distributions and distributions. If I were to give you a simple analogy, like the maps for your so imagine a journey without a map. If you're not familiar with the territory, how would you proceed without a map? So okay, it will become very difficult for us or for you. And if you're dealing with the data and if you've been able to trace a distribution for that data, your life becomes much easier. And you gain a lot of confidence in what you're doing. Then so it's the foundations and it's the building block of your entire study of a given data. And if you already are comfortable with it, just hang in for a while, and I'm sure these things will start making a sense to you. Okay, okay. Bayes theorem is not but an applications. It's nothing but an application of the conditional probability. This is a red rectangular space, is known as the simple space. It is nothing but a collection of all the possible outcomes of an experiment and let there be events A and B. Okay, these are not disjoint events. There are overlapping and the portion which is overlapping, that is the portions which is common to both A and B is known as the in A intersection B. Now, if you are going to ask what is the conditional probability of the A and B, which is nothing but what is the probability of the occurrence of A given that B has already occurred. Now, to simplify, whenever you're dealing with a conditional probability, assume that the entire sample space has a shrunk to the event which has already occurred. So now our sample space becomes this event B because we're only dealing with with that portions of the sample space where B has happened. And now that we're figure out that B has already happened, where do we find A? In these portions, this portion that is nothing but the intersection portions, you can simply write the probability of the A and B as the probability of A intersection B divided by the probability of a B. Okay. Again, if you're finding it confusing, you might ask me to rewind, or you can rewind this video recording. Okay, so we are good to go. Okay, likewise, if we were to estimate the probability of the B given A, which is nothing but the probability of the occurrence of a B given that the event of A has already occurred. Again, it's simplified by the assuming that the sample space in this case as well has shrunk to A, and now you will look for the availability of the B and an A. and that is nothing but probability of the A intersection B divided by the probability of A. If we slightly rearrange the denominators of these two equations, we arrive at this equation. So let's call okay. This question, so let's call it equation 1. So please take note of it, refer back to it because we'll be needing it as we proceed. Now that we have arrived at the relationship between the two conditional probabilities, just one more arrangement. Shifting the probability of B from the left-hand side to the right-hand right-hand side give us the equation number 2, which is this is a Bayes theorem. Okay, so congratulations, we're almost halfway through. Okay. Let's spend a little more time and try to obtain the generalized case of the Bayes theorems. What you see on the screen now is a simple space, which is nothing but a collection of three events, A1, okay, the A1, A2, and the A3. Okay, and as you can see, there are mutually exclusive and collections of exhaustive. If that's a jargon, let me help you refresh. Okay, mutually exclusive means that the occurrence of one event precludes of or negates the possibility of the occurrence of the other events. So like when you toss a coin in a given toss, you can either get heads or a tail. You cannot get a head and tail both at the same times. And what is the collectively exhaustive? Collectively exhaustive simply means that if you add up the probabilities of all these events rather, okay, this will constitute the sample space. So if you add 1 or 2 and the 3 here, you that will be the total rectangular space that you will see. A1, okay, and A2 and A3 are also known as the prior probabilities. Now, so let's say there's another event B that occurs, and if you see B has something in a common with A and a 2 and a 3, in fact, if we were to put it like this, the portion B common with A, one is one intersection B, the portion of B common with A, 2 is A, 2 intersection B, and the portions of B which commonly A3 is a A3 intersection B. Okay, so but with the seconds, if we add all these common portions once we arrive at B, um, so exactly the probability of B is nothing but the probability of A1 intersection B plus A, two intersections B plus A, 3 intersection B. Now, if you made a note of what we obtained in equations 1 on the previous slide, A1 intersection B can be written in these forms, and now if you made a note of what we obtained in the equations 1 on the previous slide, A1 intersection B can be written in these forms, and so this case with the A and A2 and A3. So probability of B can be written in these combinations, and if you're going to generalize these equations in the form of A1 where one obtains values from 1 to n, it can be read like this. Okay, please take note. Sigma here is nothing but a summations. Okay, so now we have more generalized form of the same questions which can extend into a number of the prior probabilities. Okay, okay, so it's time to put it all together, what we obtained in the equation was this. We saw, okay, so what we saw on the previous slides, which was equation 3, was this. If we put the value of the probability of B from the equations 3 into equations 2, that is the denominator. This is what we obtain, and this is the generalized forms of the Bayes theorem. But if you're finding it too heavy now, by now, you don't have to be necessarily derive it every time that you have to solve a problem. So let's look at the problems and then let's see how this understanding help us. Okay, so here's the problem. Okay, in order to manage a credit risk, a bank regularly rates each of its borrowers as a 2 or a 3 based on their credit history. Okay, A1 implies low risk and 3 implies high risk. High risk means the chance that a borrower might fail to pay back the loan amount. Now, now, this is the background of the problem based on the historical data. On an average, 30% of the customers are rated A1, 60% are rated A2, and the 10% are rated A3. What are these? These are the prior probabilities. It was found that 1% of the customers who were rated A1, 10% of the customers who were rated A2, and 18% of the customers who were rated A3 eventually become the defaulters. Okay, that is the fail to pay back. So in a way, this is the conditional probability that's given to us. Now let's take a look at what we are expected to solve if I randomly pick up the customers from the defaulters pool rather. What is the probability that we had to receive an A rating? An important observation relative to such problem. These problems could be really daunting if you read the entire problems and then try to work it out. It will be better to break into parts and take steps by steps approach. Let's see how we can do it. By step one, what is being asked? So let's first be clear about what is being asked, and let's make a note of it. This portion of the problem says if you randomly pick up the customers from the depositor's pool, what is the probability that you have or that he had received an A rating, A1 rating? And if we were to write this is what being asked. Given what we have made our choice from the defaulters pool, what is the probability that he had a rating A1? Okay. Okay. So interestingly, the moment you figure out what is being asked, you will find the problem already contains a play of it. So I mean, to say when I'm being asked, even given defaulter given even will be given in such problems. So let's have a look. If you read the text, which is colored here, okay, and let's say 1% of the customers who were rated an A1 eventually become the defaulters. Not only that you um, that you know it for A1. You also know it for A2, and you also know it for A3. It is clearly stated in the problem. This is the conditional probability piece, which is known to us. What else is known to us? Based on the historical data, on an average, 30% 30% of the customers were rated A1, 60% of the customers were rated A2, and 10% of the customers were rated A3. And these are the simplest probabilities, prior probabilities, normal probabilities. Okay, here we go, and notice when you add these probabilities that make up complete samples, which equals 1. Okay, so now for a minute, let's go back what we are doing when we are trying to derive Bayes' theorem. Okay, did we not look at something like this? All have changed here. Um, is that now that the event B refers to the filters, and we know the journal form of the Bayes theorem. So all we are required to do, having noted down all the values that are available, is to put those values in the formula. So step 3 is going to put the values um, in a formula that we have already derived. What should be the numerator? This comes from the equations 1 probabilities, which are already given to us. What is the denominator? So it is nothing but the probability of being defaulter, and in how many ways one could have become a defaulter. A defaulter is an intersection of defaulter with A1 or 2 and the A3. And finally, all we have to do is to take the ratio of the numerator and the denominator. We derive at the 3.7%. What is the terminology that we normally use? How do we identify if the Bayes theorem's problems? We would always be given a certain probabilities, which are called the prior probabilities, such as rating an A1, okay, A2, and the A3 in this case. And we saw that when you add this all up, it would always constitute the complete sample space. Okay. The second ingredients that will always be available will be a set of conditional probabilities, and we saw it very easy to figure out if you first note down what is being asked in the problem. This will be the opposite of a or the flip of it. Okay. Okay. So coming to the last part, and it's nothing but the posterior probability, as we call it, that is being asked. I completely understand that this is a tricky topic, and that's why a lot of students or the people tend to look for a shortcuts. Okay, they try to memorize the answers given in textbooks, but that's not the idea. And like I said in the beginning, these are the kind of questions that are asked to find out whether your knowledge about the subject matter is at the surface of your or surface of you have gone to some depth. Okay, the next one or we're going to discuss is the probability distributions. Okay, so let's say define the random variables with the capital X. Okay, numbers of heads heads after a pair coin. Okay, so given the definition of a random variables, what we're gonna try to do is okay. So in this video record, the discussion is think about the probability distributions. So what's the probability? So what's the probability of the different possible outcomes or the different possible values for these random variables? Okay, and we'll plot them to see how that the distribution is spread out amongst those possible outcomes. So let's think about all the different values that you could get if we're going to a flip, you flip through on when you flip a fair coin, okay, a coin, okay, okay, and 3 times you could get all heads, okay, okay, heads, okay, heads, heads, okay, you could all get heads, okay, heads, getting heads, or tails, okay, you could get head, tails, heads, you could get head, tails, tails, you would have tails, heads. You could have tails, tails. You could have tails, heads, and you could have all tails. So there's 8 equally when you do all the um. There's a situations where you have a 0 heads. So we could say what's the probability that our random variables x is equals to 0. Okay, so let's write here. Where is our x is equals to 0, or probability x is equals to 0. Well, that is this is a situation right over here where you have the 0 heads. It is 1 out of the 8 is equals to 1 of 8 equally like outcomes. So that's going to be a 1 over 8. What's the probability? What's the probability that our random variables capital X is equal to a 1? Probability X is equals to 1. Okay, so well, let's see which of these outcomes gets us exactly 1 head. We have this one right over here. We have that one right over here. Okay, here. And I think that's all of them. So let's tails. Okay. So 3 out of the 8 equally likely outcomes are provide us get us to 1 head, which is the same thing as saying that our random variables equals to 1. So this has a 3 or the 8 probability. Okay, 3, 8. Now what's the probability? I think you're getting the hang for it at this point. What's the probability that our random variables or x is going to be equal to 2? Okay, p equals 2. The 2. Well, for x to be equaling 2, that means we get 2 heads when we flip the coin 3 times. So this outcomes meets the constraints. This outcomes we get our random variables to be equal to, and this outcomes would make our random variables equals to 2. And these 3 out of 8 equally like outcomes. So this has a 3/8 probability. And then finally, we could say what's the probability that our random variables x is equal to 3? Well, how does our random variable x uh, equals to the 3? So there are only one out of 8 equally like the 1. 1/8. Okay. 8 equally outcomes that meets the constraint. So it's a 1/8 probability. So now we just have to think about how we plot this to really see how it's distributed. So let's me draw. Wait lang. Let's make me draw a so over here the vertical axis. Okay, so we have here the probability, prob and the outcomes. So outcomes. This will be the probability, and it's going to be a 0 and a 1. So you can have a hard probability larger than 1. So just like this. So let's see if it is 1 right over here, and let's see everything here. So it looks like it's an 8. So let's put everything in terms of 8. So the half, that's half. 8 is that's a fourth. It can be, that's not quite a fourth. 0, 1, 2, 3, 1, 8, 2, 8, 3, 8, 4, 8. So this is a fourth right over here, and then we can do it in the terms of 8. So that's a pretty good rough approximations. And then over here we could have that outcomes out outcomes and so outcomes, I'll say outcomes for where I let's write these yun, outcomes. So the value of x, so x could be a 0, 1 actually to the same colors. X could be a 0, x could be 1, x could be 2, and x could be 3. Okay, these are the probabilities of x, and now we're just gonna plot the probability the probability that has a value of 0 is 1/8. And so I'll make a little bit of a little more bar right here. Okay, let's go up to 1/8. So actually draw like this. So it goes up. So this one 8 right over here. So the probability that x equals 1 is 3/8. So that's 2/8, 3/8, and gets right here over. So let me do the probability of the purple color. Okay, so actually I'm using the okay, I'm gonna look like this. It's gonna look like this, and actually let me just write a little bit here. Okay. 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 So right guys, here over here is the discrete. It only takes the random variables, only takes a discrete values. It can take any value in between these things. So discrete probability or probability distributions for our random variable x. The next one, okay, so in this video, we're going to take a look at the central limit theorem. Okay, so the central limit theorem is one of the most important and interesting discoveries in the statistics. Okay, essentially what it says, if certain requirements are met that we'll talk about later, then the sampling distributions of either the mean or the proportion of the sample will approach the normal model. So before we talk about what that means, I'm talking about is I'm finding the mean or the average or the proportion of the sample of the certain amount of the objects. For instance, if I have a one dice, I can roll that dice as many times as I want. And what I expect to have happen is to get a 1 or 1/6. A 1/6 of a time and a 2 16 to 16 of the time and 3 over 16 of the time and so on. And notice I can have as many as 2 sets as I want, and I'm still going to expect. Now, if instead, if I roll a dice and then I find the average of those 3 dice, this is no longer a uniform distribution, and it makes sense if we think about the probabilities. So let's say if we wanted to have an average, remember we're finding the average if the average was 1 or something very close to a 1. Okay. The only way that I can get a 1 is to roll a 1 and a1 at a1, okay, value average 1, 1, and 1. Okay, so a1 also 3 dice, but to roll an average of 2, I could have a a1, a3, and a2. So I could have the a2 and a2 and a2 and a2. I could have an a1, okay, 2, 2, 2. Next one, I could have an a1, okay, a3, okay, a1 and a4, a1, a1 and a4, and then etc. and etc. So there's a lot of different ways that I can get an average of 2. And of course, I could also get an average of 1.5, um, 1.5 or 1.7 and so on. And so as we can see, this curve now looks not uniform, but a little bit more bell shapes. And instead, I look at the taking 20 die and then finding the average of value of 20 dice, and we can see that this is becoming more and more normal, and it's going to end up with a unimodal distribution, and it's going to be 3.5. Because that's the average that we could expect for the value of our, as the previous, that the certain requirements have to be met, and we're going to look a little bit at requirements right now. But really, once we look at specific situations or instances, I mean, some questions where the sigma is known or where sigma is unknown or proportions questions. We'll talk about these restrictions or requirements in the details for each of these distribution. But for now, we're just going to focus on a general idea. Means that is the either that the sample size has to be at least 30 or the population is normally distributed. So what the means is when we have looking at the dice, remember it look something like this, where basically had 6 bars for the populations. Well, in that case, the populations had a uniform distributions, and so I couldn't say that it was normal distributed. So what does it mean? Well, my sample size would have at least uh, 30 for me to use the central limit. Then so the example that I showed you wouldn't be quite there yet. So recall when we have the 3 dice. So our sample size has the 3 dice. It'll look normal, and then the sample size has a 20 dice look more normal. So they're saying you have to have at least 30 for the sample size of the normal enough to be able to use the central limit theorem. And the central limit theorem says that 3 things. Okay. um, three things. It says that the shape is going to be, which is super important, and of course the the greater and the n size. The greater the sample of size, the better the normal distributions approximations will be. And that will be describes that normal distributions with a mean that is equal to the mean of populations and with a standard deviation that is equal to the standard deviations of the population divided by the square root of. So let's take a look at an example here. We have the histogram that represent the population distribution. Okay. Um, Population distributions, and again, the keyword here is the population distributions of the weights of the um, um, 600 horse jockeys at a time and found the average weight of the of that means the population is 116.2 pounds and the standard deviations again of the population is 3.9 pounds. So now we're going to look at what would happen if we took samples of the 45 horse jockeys at the time and found the average weight of the 45 horse jockeys. So the first question is, can we use the central limit theorem? And if so, why? Well, remember there are two different ways that we could say we could use the central limit theorem. The first was the population, was the normal distribution. So we can see the population here is not normal distribution. We have the definite skew here. This is skewed to be right here because it's skewed in the directions of the tail. So this is not the normal distributions. However, a sample size of 45 is obviously greater than the equal to 30. And um and so yes, we can use the travel limit theorem because the n is greater than or equal to what is the sampling distribution mean. So what is the mean of our sampling distributions? Well, it it's the exact same as the mean of our populations, 116.2. Okay, what is the sampling distribution standard deviation? So well, remember, it's not exactly the same as a standard deviation. It is a standard deviation of our population divided by the square root of n. So I'm going to take the 3.9 and divided by 8 by the square of root of 45, and that gives me about 0.58. And then um, and then what is the sampling distribution shape? So again, the population shape is skewed right, but the sampling distribution shape is going to be nearly normal. And again, that is the beauty of the central limit theorem. As we can see, if I did create a histogram using the sampling distribution of the sample means of 4 samples of size of 40, now I've got a nearly normal distributions. I have at least one last question. Okay. So, and this is really just making sure you understand the basic before we really look at the what involves, which means the proportions used in the central limit area. So if you read the press pause, try these questions and then press play to see how you have a great graph that display the starting salaries for a low school graduates entering the workforce in the 2007. And then the first question says, what is the shape of the distributions? And it's kind of crazy, but really, I could say that uh, is a bimodal because I have one mode here and one mode there, or here rather. So that's the shape of the distribution. Question B. Okay, if we're looking at the sampling distribution of the sample means created from this population for sample size of 25, can I use the central limit theorem? And the answer hopefully is of course no. Remember that the requirements was either that this, which is the population, is nearly normal, or the n is greater than or equal to 30. So that is not the case for B. So no, I cannot use the central limit theorems. Okay, what about if I have the sample size of 50? Now, can I use it? Yes, so I can, because now it meets the requirements that 50 is greater than or equal to 30. And then, of course, for the 200, you bet that also. Okay, is greater than equal to 30, and then it says what would be expect the shape if of this distribution to be, and how would it prepare to the shape of the distribution in C. Well, for both C and D, I would expect a normal distributions, and now it would be, and it would it and how would it compare, because n is greater than. I would say that's going to be a more nearly normal than the distribution.